Hi, welcome to this video where I'll show how to set up the MC-CT EGB axis function block from the Control Techniques CT NC Axis interface library. Once the axis is configured, I'll demonstrate the main features of this interface using an MC-CT virtual axis as the master reference. So in terms of the connections and hardware, I've got a laptop. The laptop's loaded with Control Techniques Connect software, and it's also been loaded with Beckhoff TwinCAT XAE shell. There's then an Ethernet connection from the laptop through to the Beckhoff hardware, which in this case is an IPC, but the steps you'll find here will be exactly the same if it was a controller or PLC from Beckhoff. One of the ports has been configured for EtherCAT comms, and there's a connection through to an SI EtherCAT module, which is then plugged into a Unidrive M700, making this an EtherCAT axis. If you've got one of our dedicated servo products, such as Digitax HD M753, this interface is built into the product. However, regardless of how the interface is plugged into the product, you'll find that the steps are identical. So before we get into the demonstration, I just want to point out that all of the information on this interface and everything that you're going to see in the demonstration is actually contained in detail in this user guide. Okay, the user guide is free to download and it's linked in the description along with a link to the library itself for use in the TwinCAT environment. So if you prefer to learn from step-by-step instructions and a book or a PDF, then we've got you covered. Also, if you just don't want to take notes whilst you're watching the video, everything that you'll see is covered in this book. Okay, so let's begin. So I'm going to set everything up from scratch so you can see the full process and use the interface. So here we go. So I'll call it MC-CT EGB axis. And I'll just copy that because we'll use it in a sec. So there we go. A project has been generated, so I'm just going to do a little bit of housekeeping, get rid of all the bits and bobs that I don't want from the project. There we go, got rid of all that. So first thing that we want to do is point the project at the target, which in my case is an IPC. I'm then going to scan the network. If you find that the scan icon isn't there, it's because you're not in configure mode. So there we go, it's gone and found our EtherCAT interface on the IPC. So I'm going to click OK to that. I'm going to say yes to scan for boxes. There we go. After a few seconds, it's gone and found the drive. So drive 1, Unidrive M700, that's the product that we're working with. And then it's going to ask us, do we want to add an NC axis? And the answer to that is yes, because the EGB interface is in fact just an implementation to wrap up an NC axis. So we want one of those. I'll just say yes to activate free run. Okay, so what we've got now is our NC axis has been implemented, it's found our drive, and the comms link has automatically been made in the background between drive 1 and axis 1. Okay, so at this point you would normally switch out, go to the Connect software and begin to set up your axis, tell it what the motor map is for the motor that's connected to the drive, and tune the speed loop. But I've done that ahead of time to make this video a little bit shorter, so I'm just going to carry on with the remainder of the steps that you do after that step. Okay, so the next thing that we want to do is we want to add a place for our PLC code to live. So I'm just going to reuse the main project name and add that in. And there we go, here's our normal places. So we've got somewhere for our main program to live, and we've got our library references. So what I'm going to do first is I'm going to go in and I'm going to go and set my task time to something sensible, because it comes in by default at 1 millisecond, which is 10 milliseconds rather, which is a bit on the slow side. So let's speed that up, make that a sensible number. That's okay. Okay, so I think that's everything that we need to set up. Now let's go and configure our library references, because we can't begin to program unless we've actually set these up. So this is the next step. So what we've got to do is we've got to go in and add all of the PLC Open type libraries, which are under Add Library, Motion, PTP, and then you have to add these 3 blocks. Okay, so the EGB interface and the positioning interface require all three of these because they possess homing, and we use the TC3 MC2 advanced homing library as part of the homing routine setup. So I'm just going to go and add these. You have to add them all individually. You can't add them by a block. So let's just go through that process. Motion, PTP, advanced homing. Right, there we go. So that's everything in terms of the basic underpinning PLC Open motion libraries. So I also need to add from IO the TC2 EtherCAT library because we use SDO reads and writes to get hold of data from the drives, such as trip history and things like that. So there we go. And then last of all, we want to go and add the CT/NC Axis library itself. Now I've already got that installed in my system, but I'll just show you quickly. Library repository, PLC library repository, and then what you'd do is you'd click install, hunt the place where you'd put a copy of the library, the .library file, and then that would be installed in your system. However, I don't need to do that because I've already got it installed, and you'll find that you'll end up with a control techniques category, applications, and then CT/NC Axis interface library. So I'm going to go and add that. There we go. That's everything in terms of library references that we need to add. Now we can get on with the beginning of the program. So this program is a little bit more complicated than some of the other ones because we've effectively got two axes to set up here. Okay, so the EGB is really a wrapper around MC gear in. Okay, so this is a gear locking type application. So EGB stands for electronic gearbox. There are lots of other names, but essentially what we're doing is providing an interface layer over the top of MC gear in. Okay, so to do that we need a slave axis, so that'll be the EGB axis, and then we need a master. And because I haven't physically got another encoder to follow on my particular setup, I'm going to set up a virtual axis, which we've also got an implementation for, and I'll show you both at the same time because it makes sense. So let's crack on. We want to start off by declaring our axis refs. So I'm going to go axis 1, and that will be of type axis ref. Oops. There we go. And we want another one of those. I'll just put a little bit of space and I'll make that one axis 2. So axis 1, this is the master. And then axis 2. Ooh, sorry, I've got that the wrong way around. Oh, and I'll be slave. This one will be master. So the master is the virtual axis. So next thing that we want to do is we add our EGB. So we'll have axis 1 EGB. And that will be of type MC CT EGB axis. There we go. So our axis 2, so our virtual axis will be axis 2 virtual. And that will be of type MC CT virtual axis. And there we go. So that's those two sorted. Next thing, because I like to demonstrate these function blocks just from seeing what the inputs and outputs do in LD language, because it's well, you'll see it's a bit more convenient to do so, I need to put in a place where I can program in LD language. Now there are lots of ways to do this. This is just the way that I'm choosing to do it now. So I'm adding an action and I'll call it motion. And the language that it will get implemented in is LD. So there we go, there's a place that I'll put our motion function blocks in a second, but what I do have to do in our main is call motion. So what happens is when main runs, all of these things will be declared and available inside motion, but I do have to call motion to execute the code that's inside this place. So next thing, let's go and add our motion function blocks in. So I'm going to add 2 ENO type blocks. So I'm dragging it from the toolbox, but equally you can right click and add. Both methods work. You do get these question marks at the output even when you do turn most of them off, but I will say tools, options, TwinCAT, PLC environment, FBDIL editor, make sure that box is ticked, otherwise you end up with question marks at all of the inputs and outputs of the blocks. Okay, so let's go and specify this. So what we'll actually do is have the virtual axis first, because you want it to calculate its numbers and then pass its numbers then onto the EGB axis. So this is axis 2 virtual. There we go, there's the interface, and I need to connect it up to its axis, which was axis 2. There we go, so that's everything that you need to do to demonstrate that. Now we'll do the same process for the EGB axis, the follower. So EGB, actually that's not what it's called, axis 1 EGB. There we go. So what I'm going to do is actually minimize that so we've got enough room on the page for all of the I/O to be seen at the same time, and I will actually squeeze that over a little bit. There we go. So we need to connect our axes. So the slave axis in this case is axis 1, and the master axis is axis 2, which is being controlled by this block. So essentially, what will happen is this block, when EGB is activated, will just follow the output reference from this one. Okay, so that's as much as we need to do in order to get the kind of basic hello world stuff and to be able to demonstrate the blocks. Let's go and build that. So you can do Control-Shift-B or build solution, as I'm showing now. There we go. So that's built. There was no errors. It's crucial that it builds with no errors, because then it means that our axis ref instances that we declared here will be available to pick and to connect to our axes here. Now, what I'm going to do is I will go through the process of setting up the EGB axis, and then I will set up the virtual axis afterwards. Okay, so when you're setting up the axis, you need to go and connect it to the instance of axis ref, which is under settings. So you've got this link to PLC. You can see that the link to I/O, which is essentially linking it to its EtherCAT drive, that's already been done. That was what happened when you added the NC axis. This automatically got linked to this drive. But what we need to do now is link it to its axis ref, and we've got two in here, axis 1 and axis 2, and because axis 1 really is the EGB, there we go, we've added that. In fact, I think I can see small EGB axis. Okay, no, I think they're both right. So we've made that link, that's fine. Now what we've got to do is go and set up the encoder scaling. So we set that up in the parameter, and we've got two values, a numerator and denominator. The numerator is a number of units, and then the denominator is a number of counts that's the equivalent of this number of units. So by far it's the easiest to do everything per rev. So I know per 1 rev, the default resolution is 16-bit, which is 65536 encoder counts per rev, and I'm going to choose a number of units per rev of 1000. I'll then go and set my modulo factor to the same, which is, so if you're going to do any modulo moves, it will be 0 to 999, the position that you would set it in, should you want to do that. So that's everything for the scaling. Let's get back to the main axis, and then we'll go and set up the main properties. Now, for my particular axis, I know ahead of time that 3000 RPM, which is the maximum speed for the axis, so I'll show you if your references, maximum reference is 3000 RPM. I've already calculated for this particular axis that that is 50,000 units per second, so I'm just going to go and enter that. Copy that, because I'm going to enter it again here. There you go. I'm also going to go and set the acceleration limits to be out of the way so they don't affect us whilst we're doing the demonstration. So I'm going to go set that to 1e plus 20, which is a shorthand way of saying 1 with 20 zeros. I'm going to do the same for the deceleration because I don't want any implicit stops, because I want to be able to set whatever values I like. And last of all, I'm also going to set the default jerk to that same value, and that's for a slightly different reason. That's so that if you put 0 at the input to any of the jerk interfaces, that you'll end up with a linear profile, which is quite handy. It's better than having to put in a an absolutely massive number for the jerk, so that you achieve your acceleration in one sample. So last of all, we just need to remove the system fault monitoring, because what this will do is it will cause you an implicit stop the first time that you go, because these numbers that are actually included here probably won't work for the majority of systems, and you'll spend half an hour to an hour trying to figure out why it is that your axis is implicitly stopped just after you've started it. So I can't recommend enough turning those off. Okay, so that's everything in terms of the EGB axis. Now what I'm going to do is just add an extra axis. So I'm going to go right click on axis, add new item, axis 2. So this is going to be the kind of interface for our virtual axis. And I have to go to settings. You'll note that there's no I/O, so this isn't connected to a physical drive or EtherCAT, but we do have to link in the instance of axis ref. So I'm going to click OK to that. We don't need to do anything with encoders because it doesn't really have one, so there's no scaling there. But what we do have to do, and what you should do, is go and configure these limits to be the same as the axis that you're controlling, because there's no point in sending the master to a faster speed than the axis can go to, so you have to set all of these the same, otherwise you can end up with problems later on. So I'm going to do that. So 50,000 again. I'm just going to do this quickly. Okay, so that's everything set up the same. Now we're at the point where basically we can get everything working and begin the demonstration of the actual function block interface itself. So I'm going to go and activate the configuration. Click OK to the following messages. And in a moment it'll sort itself out and go online. Oh, one thing that I did neglect to do, which I'll just do quickly, is that you need to map up if you're going to use the freeze functionality. Come on, there we go. You need to map in the touch probe stuff. So I'm just going to double click on the axis and then go process data, click on position status. So this is information coming back from the product. Select a spare space, add new item, and then all you've got to do is select from this. So we need touch probe status, and we need, I'm going to choose to have positive edge, and because I don't know which of those that I would want, I would also add negative edge as well. This is kind of like the minimum that you need to, you know, have useful operation for like homing and when you're just trying to capture the general position of the axis. And then I'm going to choose the outputs, and then I'm going to add in the DS402, which is the underpinning control layer that's underneath EtherCAT. I need to add its touch probe control word. So there we go, that's all of that done. So touch probe will work. Let's just activate that. If you end up with any warnings about down here about touch probe, that's the reason. You just have to manually map those items in. Okay, so we're back running again. We've got our green background swirling icon, which is good. Here are interfaces. I'm just going to log in, and there we go. Okay, so what I'm going to do to begin with is I will focus on this interface, because essentially most of these inputs are duplicated here. So if I explain what these ones do, it's also kind of explaining what these ones do, because largely these references are the same between the two. So let's focus. So we've got our slave axis input, master axis input that we've set up before, and then we've got some status information here. So we've got cyclic comms okay, so we cyclically use SDO reads and writes to push data into the drive and to read data from the drive. So things like what's the trip history from the product. We've got an output here that says is the EtherCAT comms ready, that you can read, you know, directly at the output of the block. We've got one that says is the master drive on. So if I turn this one on, you can see that we can tell whether we're in a position where if we want to follow, using this axis using the EGB command, we know that our master is on and actually we can begin to follow it. If that's not on, then you shouldn't be trying to follow it here. Okay, we've got status drive on, which is telling us whether this particular drive is on. So let's do that. If I go, there we go, we can see drive on. So if I show you, if I go online, there we go. So we can see that the axis has gone from inhibit to run. Okay, so it's ready to receive some motion commands. So one thing that you will notice, and it's the same with all of the other function blocks, is that there are more or less 3 categories of input and or output. Okay, so ones that start CMD, this is commanding the drive to do something. Okay, so we've got, turning the drive on, resetting, commanding a controlled stop, jogging, homing, etc. So, when you're using IntelliSense and you're programming structured text, you can go CMD underscore and then you'll just get a nice list of the command inputs. Secondly, we've got configure inputs, CFG. So if you want to get hold of one of these, it'd be CFG underscore, hit control and space, and then you'll get the list of potential inputs to configure for the block. So this is where you'll configure things like deceleration rates, jerks, speeds, homing modes, all that good stuff that's associated with each of these commands. And other things down at the bottom, things like automatic stopping on following error, breaches, and whatnot. And the outputs, they're all STS, so STS is short for status, and they're configured into 2 basic categories. So those are Boolean outputs, so it could be anything from telling us with a Boolean state, true or false, whether or not the drive is okay, whether we're at speed, at 0 speed, whether or not any of the particular references are active or not, or which one is active, which one has got controlled, things to do with hardware limits, freezing, which is analogous with MC Touch Probe. So freeze is like a Control Techniques terminology, but it basically means position capture of the axis. We've also got error checking for the PLC open function blocks that are underneath. So this is forwarding out any errors that are seen by any of the internal blocks. So if you've got something like MC power or MC move velocity, all of those errors are kind of brought together and brought out to a single error output, so you've got a means to be able to detect if something has gone wrong. For example, if you put in a speed that's higher than the axis maximum, for example, that would cause you an error to come out here, and you'll be able to use these outputs in order to diagnose that. We've then got the PLC open state, so you can tell whether it's in error stop or whether it's in continuous motion, discrete motion, etc. We've then got some drive status here. So we've got alarms, last trip, the last sub trip related to this particular trip, drive load, then we've got a load of position information and the modulo position if you're doing anything like a carousel or something else that's a modulo positioning system. So let's have a little go with some of these references. So to begin with, in fact I'll put the camera on. There's a little bit of a delay with the feed from this camera, so it won't act immediately, but I'm just going to use the default speeds and tell this to go. If I put that back on and go view always on top, there we go. So we can see that we're able to jog. Okay, so if I jog in reverse, there we go. So I'll just show you the motion stop, what that does. So motion stop is does a controlled stop that's overriding. So no matter which reference that you've got connected, this one is the boss, this one takes over. So if I tell that to stop, it'll do a rapid stop at the rate that has been defined here. And then in order to get the axis to go again, you have to unset those, and then you can begin to jog. So there we go, that's those. One thing that I will point out with all of the main motion references, that there's no need to kind of re-execute the MC move velocity or anything like that. Any changes that you make at the interface are directly responded to. So for example, if I want to change my speed to a lower one, so say 200 units per second instead of 1000 units per second, if I pop that in, you'll see it directly. There's no re-executing or any of that nonsense that you have to do with normal PLC open function blocks. It will just take effect straight away. The same with the acceleration rate, the same with the decel rate, same with the jerk. Okay. The only reference where that's not true is actually for motion stop, because this uses MC stop and you can't change the rates or execute another instance of MC stop whilst you're in the process of stopping. So that's a restriction of PLC open. So if I stop that, then we've got homing. So the default homing is home where we are. So if I go and have a look at our position, you can see drive actual position is 2.48 something. Okay, so if I engage our home, by default it's home where you are and its reset position is 0. So I go and do that, come back down again, you can see that our actual position has been reset back to 0. Okay, so another useful thing about demonstrating it in this mode is that all of the inputs are enumerated. So that means if you're using it in LD and you're just seeing what you want to do with it, actually when you click on it, you just get a list of all of the names for the modes, for example. So we could home to a homing switch, we could home to a switch that's located on the drive rather than the switch that's this one, home switch. We could home to a switch and then a marker pulse, home to a switch that's here and then reverse to the index marker, and so on and so forth. So there's lots of different modes here, a lot of the really standard ones that you'd probably want to use. I'm not going to cover those for the purposes of this, but it's just to show that they're all there. Then we've got the positioning reference, which I will have to do a little bit of setup for, so I'll just put it in relative mode. So it will do a positional move from where it is now, and then I will just say change my target to 10,000, which will be 10 revolutions. If I go and pop that in and then command my position, this will move by 10 revolutions. So we'll leave that to complete. If you remove the command input whilst it's in motion, it will just implicitly stop. With the way that this is configured, it won't finish the positioning. If you want it to finish, you leave command position true and wait until you've got position complete. And you can see that it's finished. So next, I suppose the main reference for this, which is EGB. Let's engage that. So at the moment we've got our virtual master is on, we've got master on. There's no point in switching command EGB on. If the master that's going to control it is on, you will almost certainly end up with an implicit PLC open type error from the NC axis system. Okay, so you need this on, and then we can engage the lock. Okay, so this is now locked to the things that this does. So all I'm going to do is jog just to show. So there we go. You can see that now the virtual reference that we're getting from this axis has been passed through this interface here, and we're running with it. So if you're doing like a multiple lots of axes that you want to run at the same time from a single reference, this is one way that you could achieve that. So you could have lots of synchronized conveyor belts, for example, that would run from this one virtual reference, and then when you engage the EGB lock, all of them would be synchronized with each other and running from the same reference. Okay, so I'm just going to stop this and disconnect the EGB. There we go. So that's most of the main reference. There are a few other things to sort of talk about whilst I'm here. So you've got the ability to sort of turn on, turn off travel limits. You've got the ability to stop automatically on following error. But one nice feature that you've got down here is you've got the ability to name the axis. So what you'll see is that this name here propagates through into the drive. So you'll see that its name has been set to 1001. For those of you that are familiar with the node IDs in EtherCAT, this is its node ID that we've extracted from the axis name. So if I come back to the project and close that down, you'll be able to see, if I go to the EtherCAT tab, this is the EtherCAT address, that same 1001 number. So if you don't do anything at all to the input, it will come through as 1001. But equally, you might want to name that. So let's do that. So I will call this Nidec drive in single quotes, and I'll go and apply that. So there we go. Now it says Nidec drive. We just changed its name, and then in Connect it now says Nidec drive. So this gives you a nice way to be able to identify your specific access and where it appears in Connect. Okay. Next thing that's interesting is that actually you can see this name on the drive's display if you want to. So if I go to parameters in here and then show menu 11, you can see Nidec drive. So each of these parameters contains 4 of the characters, but it's possible to display this on the drive's display, or if you keep your name down to 4 characters, actually you can display it, the whole thing. So if you want to, and you've got one of the older keypads, you can actually direct this parameter 11 to 18, set that to 1179, and in fact you'll see the name that you've given it on the display, which if you leave it as the default, which is the EtherCAT slave node number, it will display the whole node number on there, and that's actually quite a useful thing when you're dealing with a big network and drives with displays. You can actually go ahead and view the name that's been given. So I think that's about as much as I want to kind of cover in this. Hopefully you've found this interesting. Hopefully you'll find that this is something that you can go ahead and use in your applications. Hope you found this interesting. Thanks for watching.